Hello. In this podcast, we'll talk about one-dimensional motion. We'll start by defining the basic quantities used to describe motion, look how they're mathematically defined, see how they're related to each other graphically, use calculus to derive the three kinematic equations, and we'll look at how we analyze motion using calculus. So the basic quantities defined, we have time, also known as clock time. The symbol is t. And it's time read from a clock. It's a scalar quantity in seconds. Next, we have elapsed time. The symbol is delta t. It's the change in time between the beginning and end of an interval. It too is a scalar quantity and has units of seconds. Position is represented by the symbol x for horizontal position and y for vertical position, and it's a particle's distance from a reference point, which is often called the origin. It is a vector quantity and its units are meters. Displacement is delta x for horizontal displacement and delta y for vertical displacement, and it is the change in a particle's position. It's a vector quantity and its SI units are meters. We also have velocity, symbol lowercase v, and it's the rate at which a particle's position changes. It's a vector quantity with SI units of meters per second. We have acceleration, lowercase a. It's the rate at which a particle's velocity changes. It's a vector quantity and its SI units are meters per second, also known as meters per second squared. Jerk, with a capital J, is the rate at which a particle's acceleration changes. Likewise, it's a vector quantity, and it's meters per second, or meters per second cubed. We have distance or path length, and this is the total length a particle travels. It's a scalar quantity with units of meters. And lastly, we have speed. That's the rate at which a particle's path length changes. It's a scalar quantity measured in meters per second. Let's look at the definition of the mathematical relationships. Displacement, the symbol delta x, is the particle's final position minus its initial position. For velocity and the remaining quantities, we have the average version and the instantaneous version. For average, we're talking about a calculated value over a time interval, delta t. For instantaneous values, we're talking about a value calculated over an infinitesimally small time interval, known as, in calculus, dt. The average velocity is the displacement divided by the elapsed time. The instantaneous velocity is the displacement over the elapsed time as the elapsed time approaches zero. In calculus, we know that as dx dt, or the derivative of position with respect to time. Speed, the average speed, is the displacement divided by delta t. The instantaneous speed is the derivative of path length with respect to time. Acceleration, average acceleration is the change in velocity divided by the change in time. Instantaneous velocity is the derivative of velocity with respect to time, which is also the second derivative of position with respect to time. And we also have jerk. The average jerk is the change in acceleration over the change in time. Instantaneous jerk is the derivative of acceleration with respect to time, which is the second derivative of velocity with respect to time, and it is also the third derivative of position with respect to time. I want to talk about some conventions used in AP Physics. In honors physics, we use delta t, delta x, delta v, and delta a. Typically in AP, they'll use time instead of delta time. x instead of displacement, velocity instead of the change in velocity, and a instead of delta a. Also, they'll use conventions x sub naught, v sub naught, a sub naught to refer to the value of these quantities when time is equal to 0. And then the quantities t, x, v, a refer to the value at the instant you're evaluating it. So to refer this or compare this back to honors physics, the naught subscript is similar to the initial subscript, and the quantities without the subscript are comparable to the final value. Let's take a look at graphical relationships between these quantities. First, we'll look at a position time graph. On the y-axis is the position, on the x-axis is the time. So this simply graphs the position as time goes on. Velocity is the derivative of position with respect to time, or the slope of the curve. So by measuring the slope at any point in this curve, we can get the velocity for that specific instant of time. Here are some key characteristics of a position time graph. A straight line, as shown in segment 1, is constant velocity. A horizontal line, or also known as a flat line, as shown in segment 2, is an object at rest. Uniform acceleration is a parabola, as shown in segments 3, and this can be an upward-facing parabola or a downward-facing parabola. Point 4 is an inflection point, and it shows where acceleration changes direction. And also, uniform jerk will result in a cubic function. That is not shown here. Moving on to a velocity time graph, time is still plotted on the x-axis, and velocity is on the y-axis. The velocity time graph characteristics are quite a bit different than the position time graph. We have to remember that acceleration is the change in velocity with respect to time, and so the slope of the velocity time graph will give us acceleration. And we have to remember that displacement is equal to the velocity times the elapsed time, and that is equal to the area under the curve. Let's look at the key characteristics for the velocity time graph. Section 1 shows a constant velocity and a flat line. Section 2, when an object is at rest, the flat line will be at velocity equals 0. When an object is accelerating uniformly, you will have a straight line. Okay. Acceleration changes occur at a local maximum or minimum. An object changes direction when the curve crosses the time axis. And finally, uniform jerk results in a parabola, and this is not shown on the graph. Moving on, let's look at the acceleration time graph. Acceleration is plotted on the y-axis, and we need to remember that jerk is the rate at which acceleration changes with respect to time. So the slope of the curve on the acceleration time graph will give you jerk. And then we also have to recognize that velocity is acceleration times time. So it'll be equal to the area under the curve in this graph. Again, the key characteristics. In number 1, we have constant velocity. That'll be a flat line at acceleration equals 0. When an object is at rest, as we see in section 2, the curve looks no different. It is a flat line at acceleration equals 0. Uniform acceleration is shown in sections 3. It'll be a flat line either above the x-axis or a flat line below the x-axis. Acceleration changes direction when the curve crosses the time axis, which is also known as the x-axis. And finally, uniform jerk would be represented by a straight line with a non-zero slope. That is not shown on this graph. In this next section, we're going to use calculus to derive the three kinematic equations we use for constant acceleration. First, let us start with the definition of acceleration. It's the rate at which velocity changes, or dv dt. We need to change this to a simple differential equation by multiplying both sides by dt, and that leaves us with dv equals acceleration dt. Now we need to integrate both sides from 0 to t. We're picking the variable t, so we have a general equation that we can use for all values of t. So we go ahead and set up this integral, and if acceleration is constant, this gives us the velocity evaluated at time equals 0, and t is equal to the acceleration times time evaluated at time equals 0 and time equals t. That yields velocity minus v sub naught is equal to the acceleration times time minus the acceleration times 0, and that simplifies to acceleration times t. We can rearrange this equation and we come up with equation 1 of our kinematic equations. Velocity is equal to the acceleration multiplied by time plus v sub naught, which is the velocity at time equals 0. Let's move on to our second derivation, and for this we start with the definition of velocity. It is equal to dx dt, or the change in position with respect to time. We once again rearrange this to form a simple differential equation, dx equals v dt. We integrate both sides from t equals 0 to t equals time, and that gives us these integrals. If acceleration is constant, we can substitute equation 1 from the previous slide for velocity. And notice we did that down here on the right hand side. We put in a times t plus v sub 0. Solving both integrals, we wind up with x evaluated at 0 and t is equal to 1/2 a t squared plus v sub naught t evaluated at 0 and t. And that leaves us with x minus x sub naught is equal to 1/2 the acceleration times squared plus v sub naught t minus 1/2 the acceleration times 0 squared minus v sub naught times 0. Of course, these last two terms wind up being 0, so this simplifies to 1/2 a t squared plus v sub naught t. We can go ahead and rearrange this and move the x sub naught over to the right hand side, and we're left with position is equal to 1/2 a t squared plus v sub naught t plus x sub naught. Or we can leave the x sub naught over on the left hand side and we get delta x, or displacement, is equal to 1/2 acceleration times time squared plus the initial velocity times time. Let's move on to our third derivation. So far we have two equations that are a function of time, and now it'd be nice to have an equation that we can use that is not a function of time. This derivation actually involves only algebra. So if we take equation 1 from 2 slides ago and rearrange it to solve for t, we get that time is equal to the velocity minus the velocity at time 0 divided by a. If we take this expression for t and substitute it into equation 2, which we derived on the previous slide, that yields 1/2 a times, in parentheses, v minus v sub naught divided by a, that quantity squared, plus v sub naught times, in parentheses, v minus v sub naught divided by a, plus x naught. So we can multiply terms out, we can collect like terms and simplify, and we wind up with equation 3, velocity squared minus v sub naught squared is equal to 2 times the acceleration times displacement. There is one more equation. Some books refer to this as equation 2. I'm just going to pose it as the fourth equation, and it's based on our definition of average velocity, which is the displacement divided by the elapsed time. If we have constant acceleration, then average velocity is equal to the velocity plus the velocity at time equals 0 divided by 2. This gives us 4 valuable equations that we can use for analyzing motion when we have constant acceleration. However, not everything moves with constant acceleration. And that's where calculus can be a big help in analyzing motion. So let's talk about how we analyze motion using calculus. First, let's review the fundamental concepts of calculus. First, derivatives yield rates. So if we have an expression for position and we take the derivative of that with respect to time, it will yield velocity. Similarly, if we have an expression for velocity as a function of time and we take the derivative of that equation with respect to time, it will yield acceleration. Integrals yield the product of two quantities that depend on each other. So for instance, if we have an equation for velocity changes with time, we can integrate that equation over a time interval and it'll give us the position or displacement. Similarly, if we have an expression for acceleration and how it changes as a function of time, we can integrate that equation over a time interval and it'll give us the velocity or the change in velocity. If a problem asks you for a general equation to describe the position, the velocity, or the acceleration, you're going to have to solve either the derivative or the integral. However, if they are asking you for these values at a specific time or over a specific time interval, and you don't like solving derivatives and integrals, you can use your graphing calculator to solve these problems. The key here is to remember that the derivative is the slope of the function's curve. Therefore, you can graph the function and find the slope for a specific instant. Similarly, an integral is the area under a function's curve. Therefore, you can graph the function and use your calculator to find the area for a specific time interval. Let's move on and look at a specific problem. A particle's velocity as a function of time is velocity is equal to 2 meters per second cubed times time squared plus 5 meters per second squared times time. Clearly, with this function, the particle has non-uniform acceleration, so we cannot use any of our 4 kinematic equations. So problem 1 tells us find the particle's acceleration at t equals 2 seconds. Well, we need to remember that acceleration is the rate at which velocity changes, so we need to take the derivative of the velocity function with respect to time and evaluate it at t equals 2 seconds. So if we go ahead and find the derivative of that equation, we're left with 4 meters per second cubed times t plus 5 meters per second squared. And if we evaluate that at 2 seconds, we're left with an acceleration of 13 meters per second squared. We could also be asked to find the particle's displacement during a time interval, such as from t equals 2 seconds to t equals 6 seconds. For this, we need to remember that displacement is the product of velocity and time. Since velocity is not constant, we can't simply take a velocity and multiply it by time. We need to take the integral of the velocity function from time equals 2 seconds to time equals 6 seconds. And that gives us an integral evaluated from 2 seconds to 6 seconds of 2 meters per second cubed times t squared plus 5 meters per second squared times t dt. We can go ahead and solve this integral, and we're left with 2/3 meters per second cubed times t cubed plus 5/2 meters per second squared times t squared evaluated at 2 seconds and 6 seconds. And that leaves us with a displacement of 200 meters. So this ends our lesson on kinematic one-dimensional motion. I hope you found this helpful.